I'm just making sure. Okay, yeah, we're finally recording. And first thing first, I would like to greet you all. My name is Mlamuli Makanda, and today I will be taking your lesson for grade 10 functions. And thank you for joining us. The recording is live. Let's get to it. So I did ask a question on the group on which topic I should tackle today, and I think only one person responded directly, and that I should tackle the functions. Okay. And please, guys, if I'm not audible enough, or if you would like to ask something, just raise your hand and then you'll unmute yourself and ask whatever you want to ask. Okay, so today we'll be dealing with functions. As you can see, this is lesson one, and I'm sure some of you are wondering why there's a word relationships there. The relationships are a big deal in nowadays. So basically, relationships are everywhere, even in mathematics. And today you are gonna see that functions are basically a way to represent relationships between variables, between numbers, between any other factors. There are different ways that we can represent relationships. And please, guys, do raise your hands if I'm also speaking fast so that I can maybe reduce my pace. But anyway, let's continue. Relationships can be represented in what? In tables, with tables. They can be represented with formulas, formulas, and please forgive my handwriting. With formulas, they can be represented with graphs, of which is what we'll be doing today. Representing relationships in graphs. But these relationships are between numbers and variables. For an example, let's say we have this graph here, just a simple graph. I want to show you that functions are basically relationships. Let's say we have just a simple straight line graph here with a positive gradient, of course, with a positive gradient. Okay, let me put like this here. Let me put like this with a positive gradient. So basically, what this graph says is that when we are moving to the positive side of the x-axis, this is our x-axis and this is our y-axis. When we are moving to the positive side of our x-axis, or when we are increasing the x-axis, simultaneously or under the same breath, the y-axis are also gonna be increasing. As we are going in this direction, uh, or in this, let me just put it like this with a red marker. When we're going in this positive x direction, y will also be increasing. So basically this is what is represented by this simple graph here. It's a relationship between the x and the y direction, and the same thing happens if we are going in the negative x direction, whereby the x is decreasing and decreasing and decreasing again and again. The same thing will be happening for what? For y. Y will also be decreasing. Y will also be decreasing. So this simple straight line graph here represents a relationship between the x and the y values. So we do have a general formula. Maybe let me not clear this. We do have a general formula to represent the relationship for this kind of graph, which is a straight line graph. So today we're also going to talk about the four basic functions. The four basic functions, which are namely, number one is your straight line. And forgive my pen here, sometimes it just likes to act, which is a straight line. Straight line straight line function or straight line graph, sometimes just called a linear function. sometimes called a linear function. And then we're also going to talk about a parabola, a graph that's a parabola, which is sometimes called a quadratic function. Quadratic function. And we're also going to introduce the general formulas for this function and how we extract those things from the graph. And then thirdly, we're going to talk about the hyperbola or the hyperbolic function. Hyperbola. And then we're also going to talk about the exponential function. Let me just put function here. Okay, so let's start with the straight line function. I'm sure some of you are already familiar with this, with the straight line function. Let me just say the linear function, and some few things that we need to know about the linear function. So the general formula for the linear function, as you may be well familiar with it, it's y is equal to mx plus c. Y is equal to mx plus c. And what do these things represent? Oh, another thing just to mention, remember that we said we talk when we are dealing with functions, we are dealing with with relationships. So here we will be dealing with the relationships between the x and the y values. So we are looking at the relationship between this x here and this y values. Say maybe when x is increasing, y will also be increasing, or maybe when x is decreasing, y will also be decreasing. So this is what we're dealing with here in this linear function. Okay, we do have this c here that you see here. So the c basically represent the y-intercept. Y-intercept. The c represent the y-intercept. So what does that mean? Where the graph of x is where the graph of y is equal to mx plus c, or the linear graph, where x is equal to 0, that's where we essentially find the y-intercept. As you can see, where our x is equal to 0, this is where we find the y-intercept. So basically this is where this graph cuts y. Let's come back here. Here is the intercept that I'm talking about, where the straight line graph cuts y. And as you can see here, when we are moving in this direction, as I'm highlighting here, x is becoming positive, and here we do have our origin. Where x is equal to 0 and y is equal to 0. So if you just move from here and move upwards, you can see that this is where x is equal to 0, and that is where we find our y-intercept. You can simply just substitute the 0, if you do want to prove this, into this general formula here, where y is equal to m into 0 plus c, and then you see that indeed y is equal to c. And then we do have the m there. The m represents the gradient, which is sometimes called the slope, or the slope of the graph. So it depends. It simply says how steep is our graph, or how steep or how gentle. When the gradient is big, of course that means our straight line graph will be more steep, like this, will be more steep. And then when our gradient is gently or is small, that means that our graph will be gently, like this. Those doing geography will be familiar with this. So this is basically the straight line function, the relation which represents the relationship between the y and the y and the x values. Okay, let's move on. Next, we said we're gonna touch on the parabolic functions. Parabolic functions. Okay, so for the parabola, which are sometimes called the quadratic functions, we do have the general formula for the parabola. Let me choose a different color, which is y is equal to a x squared plus c, x squared plus c. Okay, it's somewhat similar to the straight line function, as you can see, and still we are dealing with the relationship between the y and the x-axis, between the y and the x-axis. And then let me write the just the general graph for the parabolic function. For the parabolic function, just a general representation so that you can see what we are talking about, so that we can see. So this is our function, like this. So this is the general representation or graph for the parabolic function. This is the general formula here for the parabolic function, and this is just the general graph. Okay, another thing that I would like to mention about the functions is that functions are continuous. As you can see, that's when we draw the functions, we also include these arrows here. These arrows here, we have these arrows because functions are not ending just because the graph or our page is limiting us. It doesn't mean that the function ends here. It doesn't mean that the function ends here. As you can see those arrows, it means that the function keeps on going in this direction. It keeps on going in that direction. And for a parabolic function, you can already see that as we are moving up in the positive y direction, we are also expanding. So this function is essentially moving in the positive y direction, and also even though it's not very clear or sharp, but there is a movement also in the positive x direction. So when we are moving in the positive x direction, y will also be increasing. Remember, we said functions are just relationships between variables or between numbers. So here we are learning the same thing that we learned here in the straight line function. That's okay. When we are moving in the positive, let me maybe include numbers so that you can see. We have our origin here. Let's say it's maybe 1, 2, 1, 2, 3. When we are moving in the positive x direction, here, let me also 1, 2, 3. Okay. You can see with the function here, when x is equal to 1, y is equal to what? Since it's the origin, is equal to 0. But and then we move where x is equal to 2 here. What are we seeing? We are seeing that y is equal to 2. Y is also equal to 2. So what I'm trying to show here is that as we're increasing the x values, the y values are also increasing at the same time. So that's the relationship that is represented by this parabolic function. Okay, and then back to the formula. So here in our formula, we do have that c. What do c represent? As I was telling you, that the parabolic function is very similar to the straight line function. C also represent C is equal to or maybe not put equal to here, but basically C is our y-intercept again. y-intercepts. That's what I'm trying to write here. Y-inter is our y-intercept. And remember, where do I say we find the y-intercept? Whereby x is equal to 0. Then let's come back to our graph here. This is where x is equal to 0 at the origin. So basically, this is where we're gonna find our y-intercepts graphically or graphically. So C represents the y-intercepts, and then we also do have A there. So A, uh, the easy way to know, remember, it represents the shape or the direction that the parabolic function will be facing. So in this case, if A is positive, we're gonna have something like this function that we do have here already, a positive parabolic function, a one that's facing up. So okay, maybe let's just say smiley face, smiley face is represent a positive a, and then sad face, when our function is facing down, that represents a negative a, and negative is negative a. Okay, so that's about the parabolic function. The parabolic function. Let me see if there's something that I didn't include. Okay, I think I've covered the things that we need for now. Then we can move on to the hyperbolic function. The Okay, my pen sometimes gives me a problem. Please bear with me. Okay. Hyper. I'll just say hyperbola. Okay. So the general formula for a hyperbola, and still we're still dealing with just the relationship between the x and the y, between the x and the y values, or the x and the y variables. I think once you start getting around that and start understanding that functions are basically a mathematical ways to represent relationship between things, between things. So the general formula for a hyperbola is y is equal to a over x plus q. This is our general formula for the hyperbola or the hyperbolic function. And then let's also draw the graph of the hyperbola. Of the hyperbola. Of the hyperbola. So generally the graph of the hyperbola looks like this. Okay. This is the hyperbolic function. And something that you should note here, even though we are not getting into it like right now, is that this hyperbolic function, there are some places that it doesn't touch, which is a contrast when you compare it with the parabolic function, where we were talking about the intercepts, the intercepts whereby the function will cut the x-axis or the y-axis. Here we have something different, whereby the graph, there are some places that it doesn't touch, that it doesn't touch. And then graphically, or by the formula that is represented by this value that you see here, q. So instead of having c, which represent the y-intercept of the graph, now we're gonna have q, which represents something that we call an asymptote, and an asymptote, So this is what we call okay. And then for this formula, Q represent a horizontal asymptote, you know, whereby it's a horizontal asymptote. Horizontal asymptote. Asymptote. We don't touch that place, or we don't touch that value in the graph, you know. And then usually you will see on your papers that we do maybe have something like this, you know, something like this to represent our asymptotes, you know. So, and then it's represented by Q. So it's where y is equal to Q. That is where we find the horizontal asymptotes. And then if we go take a step back and look at that formula, what will make our y equal to Q? Our y will only be equal to Q if our x is equal to 0. If our x is equal to 0. That's where we're gonna find that's the only situation that will make y equal to Q. So let's take the formula again. Y is equal to A over X plus Q. And then we substitute the X. A over 0 plus Q. So anything divided by 0 is what? Is 0. So hence what y was saying y is equal to Q. This is our horizontal asymptote. This is our horizontal asymptote. I forgot to put the arrows here. The arrows here. Okay. Because our function, the function will keep on going, you know, until infinity. You know, the function will keep on going. It doesn't end here. Don't look at the function and see it's ending here. It's because of the space and because we are limited by the resources. But the function keeps on going. And then yes, so that is that. Okay, let's go into the exponential function, and then we're gonna deal with the domains and the range. So this is the exponential function. So today we're only gonna deal with these main four functions. Okay, and then the general representation for the exponential function is written like this: y is equal to ab to the exponent x, or to the power x, plus q. And as you can see with q, that's okay. This function is very similar to the other function that we just dealt with right now, you know, that we just dealt with right now. So you can maybe already tell or assume, of which would be correct, that q, that in this function, we're also going to have an asymptote, you know, a level that the graph never touch. It may approach, you know, but it will never touch that level, you know. So we do have q here, which would be our asymptotes again. Okay. Asymptote, which will be our asymptote. And then here's the general graphic representation of the asymptote of the exponential function. Okay, is like this. Okay, like this. Yes, this is x and y. So here we can just, with this general representation, you can see that, okay, the x is the asymptote of this graph, of which is not always the case, but for this sake, you can see that it doesn't touch this level. Or maybe let me put that line again so that you remember that broken line. which represents our asymptotes, you know. And another thing that we do have here is the y-intercept, you know, whereby x is equal to 0, you know, where x is equal to 0. So it's gonna be a different number, you know. It's not something that you can just look from at the formula and then find it. But we can substitute here, you know. We can substitute a b to the power x plus q, and then if we will have maybe a value, if we are given a formula, we'll have a value of q, of which is our horizontal asymptote, and then let's substitute here just to find the y-intercept, whereby x is equal to 0 is going to be a to the power of 0. I'm sure you have done the laws of exponents, of raised exponents and sets. You know that if something is raised to the exponent 0, it's automatically becomes 1, you know, it becomes 1. So here we're gonna have y is equal to a times 1 plus q. So if we had the values of a and q, we can simply find the y-intercept, which could be maybe, let's say, 17 or whatever. It's going to be a different number each time, you know. Okay, I also want to touch on something here that I'm only remembering now. For the parabolic function here, you can see that it does cut the y-axis here, of which is the y-intercept, but we also have values whereby the graph cuts the x-axis, you know, the x-axis, whereby y is equal to 0. So, and how do we solve for that? Let's bring back the general formula. Y is equal to x squared plus c plus c. Remember, c represents the y-intercepts, and then we equate this to 0 plus c, and then we basically have to solve for x, you know. So you can see that maths is interconnected. This is something that we learn on algebra, you know, but you also gonna apply it here on the function. If the question were to ask you to find the x-intercept, okay, you can continue and say x squared is equal to minus c. Then depending on the values that you're gonna have at that point, yeah, you can solve for the x-intercept, you know. And the same is true for the straight line function or the linear function. We do have the y-intercepts, whereby is the place where our function cuts the y-axis, and we also do have the x-intercepts, whereby is the place whereby the function cuts the x-axis. And you know that when we're dealing with intercepts, if you want the y-intercept, we equate x to 0. If you want the x-intercept, we equate y to 0. And then another thing that I want to touch on here, since I'm already back here, that I touched on a little bit, is that our function or our graph is continuous. You know, this function is continuous, keeps on going in that direction, and also in that direction. So as we know the continuous nature of function, there are two things that we can determine from the function. And those two things, maybe you have heard about them already, is what we call the domain and the range. You know. So with the domain, we are dealing with the x values. You know, the domain correspond with the x values. Or maybe what you can do, let me write this range here. Maybe you should memorize, you know, not condoning memorizing, but if it helps, it helps. The range, you know. So I'm writing this G as a big G or a small G like this, which is similar to the way that we write our Y, So by just looking at this, you can see that's okay. The range goes with the Y axis or with the Y values, So the range goes from down here, to up here. That is our range, G similar to Y, we're dealing with our range, and then you just know it's okay. The opposite is the X values, which is the domain, And then the domain for this straight line function that we have here, you can see, as we said, that okay, the function is continuous. It continues up until if we go to this direction, and we always start with the small value when we are representing the domain. It obviously goes up until negative infinity, and also it goes towards, if we come in this direction, the number just keeps on getting bigger and bigger. It goes to positive infinity, and then the way we represent that, we can say X is the element uh, of real numbers, or we can simply say X is the element of round brackets, since we are dealing with infinity, negative infinity, up until positive infinity. So this is the domain for this straight line graph or straight line function. And then let's come to the range. So for the straight line function, you can see that the graph keeps on going down and down and down again and again. The value of Y keeps on getting smaller and smaller and smaller again. That means we're going into negative infinity. And then above the x-axis, the graph is continuous. It keeps on increasing and increasing again and again, which means we are going in the positive y-axis, positive y values up until positive infinity. So for the range will be to the similar to the domain. So y is the element of real numbers. Not sure if my representation is good. So y is the element of negative infinity up until positive infinity. So this is our range. Y goes with range, X goes with domain. Okay, then let's move on. Okay. So remember, I said something about the functions being continuous. That is very important. As you would see right now, when we are dealing with the range of the parabolic functions and the hyperbolic functions. Okay, let's start with the domain. We said the domain, we are dealing with what? We are dealing with the X values. And I've mentioned that even though this parabolic function is facing up, but it keeps on increasing. The X values keeps on increasing, keeps on getting bigger and bigger when we're going up and in that direction. So it's something like this when we're going in that direction, and the same happens here. The negative X values, when we're looking at this direction, it keeps on decreasing. It keeps on decreasing. It keeps on decreasing, So you can already tell that's okay. The domain for the parabolic function will be similar to the domain that we just dealt with of the straight line, because we are going from negative infinity to positive infinity. Even though graphically it doesn't look like that, but that is the case, because the parabolic function is increasing as we go to the positive x values, and it's decreasing as we are going to the negative x values, even though it looks like it's just facing up, but the values keeps on increasing, even though the increase may be very incremental. So let's go to the domain. Our domain, we're gonna say X x is the element x is the element of real numbers. Okay, x is the element of real numbers, or we can use that representation again. X is the element of negative. We always start with the small one, negative infinity up until positive infinity. So it's basically endless. And then let's deal with the range. With the range. Remember G, similar to Y. So okay, with the range here, let's go back to the graph here. For this one in particular, we can have a graph that's spacing down, of which will have a different range from this one. We do have that intercept. We do have that intercept there, and then we have this y-intercept, of which will be a definite value. So this graph of this parabolic function, it doesn't exist here. From this y-intercept going down, it doesn't exist. It doesn't exist. For from the y-intercept going down, it doesn't exist. So we don't have that parabolic function from the y-intercept going down, but it does exist from the y-intercept going up. So you can already tell that our range is no longer gonna be infinity, but it's gonna be some definite value. It's gonna be some definite value, and then going into the positive infinity in this case. And then the way we can represent the range, we can just say, or maybe let me just give this intercept a value for the argument's sake. Let's say maybe this intercept is -2. Let's say the intercept is -2, so that you can clearly see. So when we are going down, it's -3, -4. This graph that we are dealing with here doesn't exist. It's not there. So it only exists from the values, for the values going from -2 upwards. So for any value that is greater than -2, that is where our function exists. So the way that we are going to write our range is gonna be y is greater or equal to -2, of which is the what? Y intercept. Just as I didn't just want to write y intercepts instead. I think you'll understand more easily when we're dealing with the specific value. Okay. So that's the range. So it's y is greater or equal to, and I'm saying greater or equal to because we also include that intercept there. That -2, we also include it. It's included in this function. So that's why we're starting from it and then going above is for the y function. Okay, that's the domain. And another way that we can represent it is gonna be, let me see if I can move this thing just a little bit so that I can also include another representation for the range of the parabolic function. We can say y is the element of, now we're dealing with the number, always starting with the smaller one, of which in this case is what? Is -2 and the square brackets, and then our function goes towards to the positive infinity. Positive infinity, round brackets. Okay, so that's the domain and the range for the parabolic function. That's the domain and the range for the parabolic function. Now let's go to the hyperbola, and we're also gonna be looking for the very same thing, of which is the domain and the range. Domain and range. So we're gonna have something a little bit interesting here. So for the domain, we are dealing with what? We are dealing with the x-axis. Domain corresponds to the x values, and then range y values, y values. Okay. So when we come back to the graph here, and just look graphically, you can see and remember that the functions are continuous. That is very important. You can see that we are going in that direction, continuously. So we are basically going into the negative x values, right up until what? Negative infinity, because the graph just doesn't end there, so it's negative infinity. And then but something interesting here, there is this y-axis whereby x is equal to 0. We do have our vertical asymptotes for this hyperbolic function. So the this hyperbolic function doesn't touch the x-axis, so it doesn't touch the x-axis. So the x is equal to 0. No, I'm making yes, x is equal to 0. Okay, the y-axis is just the way I said it. The y-axis doesn't touch the y-axis, whereby x is equal to 0. So for our domain, okay, and then we jump into this side, you can see that the hyperbolic function is getting bigger and bigger, or is going in that direction, of which is the positive infinity. Positive infinity is getting bigger and bigger. Okay, so for our domain, we're gonna say x is the element of negative infinity up until positive infinity. But x can never be equal to 0, because that is our asymptote there. And then let's go to the range. Let's go to the range. For our range, it's basically the same thing. We're going from the negative y values. We're going from the negative y values to the positive y values. So we are going from negative infinity. So it's negative infinity up until positive infinity. But we do have that red line there, that asymptote, whereby our graph is discontinuous. Once we reach that level, our graph is discontinuous. It doesn't touch that red line there, of which we say it's a what? Is that q value? Is this q value, of which is our asymptote. So the way that we write the range, y values, we're dealing with the y values, that's your range. G similar to y, that's the range. Okay, so for our range, we will go from negative infinity up until positive infinity, round brackets. But we said what? We said y can never be equal to, y can never be equal to q, of which is the horizontal asymptote, because our graph doesn't exist there. Okay, and then let's come to the exponential function. Okay, so for the x values, or for the domain, I think you can pretty much tell it's very similar to the other ones. It's very similar to the other ones. For the domain, this is the domain. It goes from domain. For the exponential function, you can see that the function is getting bigger and bigger, more positive and more positive, and it's getting smaller and smaller in this direction. So our graph goes from go from the negative infinity up until the positive infinity. So that is our domain. That is where we will find the x values all the way from the negative infinity up to the positive infinity. That is our domain. So we will say x is the element of negative infinity up to positive infinity. Very similar to the straight line and very similar to the parabolic function. And then for the range, our y values, you can see that's similarly to the hyperbolic function, we have an asymptote here, a value that our graph never touch. That's our function never touch. So we gonna have that value is represented by what? By q, here, as we can see. This is our asymptote. So from q below here, as you can see, we don't have the function. Look at that red line. That red line is not there. From the asymptote, from that q is not there. So our graph doesn't exist here. So we're never gonna have a case whereby now we find you representing a range. That's maybe from negative infinity to positive infinity, because it simply doesn't exist. Even by just looking at it graphically, you can see that our graph doesn't exist there. So what we do instead, let me put a value again, maybe you understand easily. Let's put a value here. Let's say maybe, let's just say it's 1, for argument's sake. This is where y is equal to 1. That is our asymptote. So when I'm saying y is equal to 1, I'm also saying q for this case is 1. Q for this case is 1. But for our range, our graph is above the asymptote. So y is greater than q, or greater than 1. I'll just put q, is greater than q. So another thing to note here, remember, for the hyperbolic I said, or for the parabolic I said, is greater or equal to, because the graph does in fact exist as -2, or does exist at that y-intercept. But for the exponential function, the graph will always be above the q, will always be above the asymptote. So hence why I'm not saying y is greater or equal to q. Y is greater or equal to q. Okay, I think we can do questions now. I've covered the basics. Let's see if with the information that we have here, we are able to answer some question. Okay, maybe just to mention one thing is that before we move on. Okay, let's say maybe we had to plot this straight line function. We're gonna need two things. Each time we are plotting a straight line function, we need a what? The gradient, which is the m. I did touch on it a little bit. We need this gradient, if we were to plot. And the way that we find the gradient, if I remember very well, m is equal to y2 minus y1 over x2 minus x1. So this is the way that we find the gradient. This is the way that we find our gradient. So this y2 and y1 simply represents our coordinates, and we also need a coordinate. Maybe let's say we have coordinates a here, of which will be our x, let's say maybe 6 and 8. We need a gradient and a coordinate. Then we can plot our function. If we have two coordinates, it's even much better. And another coordinate that we can have, it's actually the intercepts. Whereby, for instance, here x is equal to 0. Let's say this is our b coordinate. X is equal to 0, and then y is equal to, no, I'm making a mistake. This is y. I'm talking about this blue one right here. it's y that is equal to 0, but x is equal to some value. I'll just call it x1, and then y is equal to 0. Y is equal to 0. Okay, we will look at some questions now. We will look at some questions. Okay. Let me see if we can find something. If we can find something. I think I downloaded a question paper, if I'm not mistaken. A question paper. Let me see. Yeah, this one. Did I download it? So this will be 10 November 2018. Let me try to add that. We'll just do an exam question because I tried maybe to find some simple question, not exam questions, but I couldn't find them. But next time I promise to have some simple questions that will deal with the specific concepts like in depth, before we get into the exam questions. But just for the sake of today, we will do this question paper that I found here. Maybe I can even touch on other topics a little bit. Yeah, but this is the question. Oh, let me just screenshot it. Let me just screenshot the question. Okay, I got it. And then question 5. Question 5. And then also question 6. So if you know those basic things that we have just talked about right now, you would see that it becomes rather very easy to answer these questions, because it's basically what we have learned. We deal about the domains, the intercepts, you study the equation that you are given and you say, okay, this equation is for an hyperbola or it's for a parabola, and then Gucci, you will have an intercept, or that will have an asymptote, then you just work from there. Okay, let me drop this. Okay, hopefully you can see. It's not very visible. Let me see. I'm trying to make it as visible. Okay, let me also drop in the other direction. So that it becomes, yes. I think that's decent. I think that you can see. But I'll also just read the question for you guys. So the question says, sketch below are the graph of f at x is equal to ax squared plus q. You can already tell just by looking at this that we are dealing with what? We are dealing with a parabolic function. Remember that, and of course we are given in the general form here, f at x. Where is f at x? So you can tell already that we are dealing with a parabolic function, and then when you look at this graph here, you can see this is our parabolic function, and it's even written a small f here just to show you. And g at x is 1/2 to the power x minus 4. And then just by looking at this equation, you can remember, you can simply remember what we just introduced. AB to the power x plus q. So this is this general formula. So you can simply tell that we are dealing with an exponential function. And then just a few things to remember. We do have this q here is our, when we're dealing with the exponential function, is the asymptote, the place or the value that the graph will never touch, you know. And then with the parabolic function, instead of an asymptote, to have a what, we have an intercept, you know, we have an intercept, you know. And then just by looking graphically and remembering what I already told you, that if our parabolic graph is facing down here, set face is facing down here, you can already tell that our a value is gonna be what? Our a value is gonna be negative. It's gonna be negative, you know, because our graph is facing down. Our graph is facing down. Okay. Now, a and b are the intercepts of f. A and b, a and b, a and b intercepts of x, so x intercepts of f, yeah, okay, are the x intercepts of f. The graphs intersect at a, you know, the graph intersects at a and point e. Where is point e? And point e, it's 1. Oh, okay, and point e lies on the f. I thought they also intercepts here, so that's why I was a little bit confused. But and point e lies on the f, on the f function on this graph. This is our point e there, and c is the turning point of f. C is the turning point of f, and d is the y intercepts of g, and d is the y intercepts of g. This is our d. Okay, so write down the coordinates of d. Write down the coordinates of d. So d, we find it on the exponential, on the exponential function, you know. So let me put this here now. This is the exponential function, 1 over 2 x minus 4, x minus 4. And what did they tell us about d? Is that d is the y-intercept of g. D is the y-intercept of g. So that means x automatically is equal to 0 here, you know, because the intercepts, for the y-intercept, x is equal to 0. Remember, I told you that. And then for the x-intercept, y is equal to 0. So we already have the first value for the coordinates of d, you know, for the coordinates of d, because here x is equal to 0, you know. So at the origin, that's where we find the intercepts. That's where we find the intercepts. So what do we have to do right now? We have to find the only value that we have to find here is the value of y, or of g at x, where g is equal to 0. So let's come here. G 0 is equal to 1 over 2 to the exponent 0 minus 4. So right now we're looking for the y coordinate. So g at 0 is basically that y coordinate that we're looking for. Let me just put y now, so that you can see. So anything raised to the power of 0 is 1. 1 minus 4. Y is equal to minus 3. So this is our y coordinates. Therefore, d is 0 and minus 3. D is 0 and minus 3. And it makes sense. D is at the intercept, is where the graph intercepts. The y-axis is where this exponential graph cuts the y-axis here. And then also another thing just to see that we are correct is that we are looking at the values below 0. So it makes sense for the y coordinates to be negative. And then what are they asking next? What they are asking next is the range of g. That is 5.1.2, the range of g. So for the range of G, remember when we are dealing with the range, we said what? Range Y, you know, big G or this hook here on the small g should remind you that we are dealing with Y values. Y values, you know. So since this is an exponential function, we do have an asymptote, you know, and here it's represented by that dotted line that I was drawing while we're doing just a general formulas. And then, so what we have to do is to find that y asymptote first. Okay, let's just write our equation again. But you can already say just by looking at it graphically, you know, what is gonna be our what is gonna be our horizontal asymptote. You know, we can simply go back to that general function, because even by observation you should, once you understand the general formulas, even by observation you should basically just be able to see by looking at the graph or by looking at the formula that this would be our asymptote. Okay, it's the exponential function. Here is the q, here is our q, this is our q, and then what do we have here? We have this, you know. So hence why it's 1 mark, because we are supposed to just do this thing by observation, you know, by observation. So you are simply supposed to do this thing by we are looking for the range, you know, but I was just mentioning that thing of the uh because it's gonna help us formulate our range, you know, for this exponential function. This is the function we are looking at. This is the function that we are looking at, you know, and this is our asymptote. You know, this is not the range now. You know, I was almost confusing myself. This is the asymptote. This is the asymptote. So for our function, when we just look at it, you know, we have -4 here. You can see that our function approaches this value, but never touches it, you know, never touches it. And you can see already that our function only exists above this value, you know. So it doesn't exist below this value, unlike this parabolic function that exists even below that asymptote. You know, we are only looking at this function. It doesn't exist below that -4, below that asymptote, you know. So that should tell you that the values of y for this function only above the will be only above the asymptote. So y is greater than -4, not greater or equal to, but just greater than, you know, just greater than the -4. So this is our range. Okay, let's carry on with our questions. Let me add the other picture. I think we're going to 5.2 now. And then let me drop it so that you can see of already. Yeah. Okay. And then we are in this question now. Question 5.2. So they are saying calculate the coordinates of coordinates of A. We have to go back to the graph again, or they are looking for these coordinates. And what do we have? we do have the function, the equation for g, but for the parabolic function, we don't have the equation, but they already told us that um a intersects, the graph intersects at a and point A. Okay, a is a what for this function is the x-intercept for the exponential function for g. A is the x-intercept. This is our g at x. A is the x-intercept because this is where the function of g, this function cuts the x-axis. So that's the first thing. That we should note. And then when the graph of g intersects or cuts the x values, what did we say about y? Will be equal to, y is gonna be equal to 0. Y is equal to 0. So you can see that you already have your what you call this thing. Your you already have your coordinates, just by understanding where the coordinates is located and understanding those. That's okay. This is the intercept, and then at the intercepts, for x intersect, y is equal to 0, and then let's come here and answer the question. The coordinates of a is 2 marks. So let me bring back the formula. X y or z x is equal to g x is equal to 1 over 2 to the exponent x minus 4, if I remember. Yes, minus 4. We already have the first coordinates, of which y is equal to 0. And then we're looking for the x coordinates. So what are we going to say here? Y is equal to 0 because it's the intercept. It's 1 over 2 to the exponent x minus 4. And then we transpose here. We're going to have 4 is equal to, I'm sure you've already done this, but I'm gonna just remind you, anything when we have something like this, 1 over 2, we can write this as what? As 2 to the exponent 1. Hopefully you still remember that, but we're gonna touch on it if you don't remember it. If we have 1 over 4, we can write it as what? As 4 to the exponent minus 1. So this is a different way of writing functions. I'm not sure if you did it in grade 9 or you did it this year. If we have 1 over 8, it can be written as what? 8 to the exponent minus 1. So that is that, because we're gonna need that right now here. So this can be rewritten as 2 to the exponent minus 1 x. And then if we have this case here, if you remember the laws of exponents, we just gonna multiply minus 1 with x. Okay, so we're gonna have 4 is equal to 2 to the power of minus x. And then what are some of the ways that we can write these parts of the equation like differently? We can express 4 in terms of 2, in terms of base 2, and then when we go back to the laws of exponent, when the bases are equal, we can simply also equate the exponents. So we can write this as 2 to the exponent 2 is equal to 2 to the exponent x. And as I was just telling you right now, is that if the bases are equal, these two are equal, we can also equate the exponent. Therefore 2 is equal to minus x. Therefore x is equal to minus 2. So finally, our coordinates of A, right? Coordinates of A will be -2 and 0. -2 and 0. Those are the coordinates of A, you know. So in the exam, there is no need to write all these steps. I was just writing them because also introducing the concepts, but in the exam there is no need for that. You can just uh plug in plug in your values and then find the find the answer. But it's also a good practice just to remind yourself, it's okay, this represent the intercepts, and then for the intercepts, if we're dealing with the x-intercept, y is equal to 0. And then let's move on to this question. 5.22. We're looking for the values of A and Q. A and Q, and it's how it's 4 marks. So we're gonna have a few steps here. Since it's 4 marks, we are looking for the values of A and Q. So it's for the parabolic function. It's for the parabolic function, of which is f at x is equal to ax squared plus q. Ax squared plus q. Okay. This is the general term that we are given. And if you remember, what did we say about q? Is that q is our, for the parabolic function, q is our intercept. This is the intercept. It's where the graph will cut, will cut our axis. So q will be here. Q will be there. Okay, so what do we have here? So wait, is there y-intercept? Not mistaken. No. Q. Okay, f at x. What do we have also? Our graph also goes here. We do have that coordinates, and then B are the x-intercepts. Okay, we have coordinates A, so we have a coordinate, and then we have two coordinates actually. We have two coordinates. We have two coordinates, of which is 1 and 3. Okay. I feel like we're gonna have to use some simultaneous equations here. So it's also good to be good in that. F at x is equal to A at x. Okay, we can just start by the coordinates that we do have right now, of which is what's that first coordinates? It's E1 and 3. E1 and 3. E1 and 3. E1 and 3. Okay, so our graph of f at x. Okay, let's substitute. Just gonna have 3 is equal to A into 1 cubed, squared plus q, and then 3 is gonna be, okay, equal to a plus q. A plus q. This is there. We can call it equation 1. And the reason why we call it equation 1, because we still have two unknowns here. So we cannot solve directly for any of the values right now. And then let's come here. We do have that other coordinate, the A that we were looking for previously, that other coordinate of which is -2 and 0. You should note that the graph of F also passes through that coordinate, also the graph of G. But right now we're dealing with the graph of F. So let's come here, gonna say 0, of which is our Y. We're using this coordinate right now, coordinates A, to get our second equation, and then we can solve simultaneously. A into -2 squared plus q. Okay, then this means that 0 is equal to A And remember, if we are squaring a negative number, we're gonna get a positive number because negative by negative is positive. So here we're gonna have 4 plus q. Therefore, our q is equal to, just rearrange, negative 4a, negative 4a. That is our q after rearranging. And then what do we do? This is equation 2. We substitute equation 2 into equation 1. Okay, so q is equal to minus 4a. Okay, let's move here. 3 is equal to a plus q. That's equation 1. And then we have q is equal to minus 4a. Q is equal to minus 4a. Okay, let's substitute minus 4a into the place of q. 3 is equal to a plus minus 4a. Okay, and then 3 is equal to, so it's basically 1 minus 4. We have 1a here, and then we have minus 4a. So it's 1 minus 4a. 1a minus 4a, that is gonna result in negative 3a's, and then we divide by negative 3 on both sides, and then our a is equal to negative 1, is equal to negative 1. So we've just found the value of a. And then what we can do right now, we are asked to find the value of q, right? So we can simply substitute back this negative a here, in order to find the value of q. Is minus 1. So q is equal to 4. Q is equal to 4. Q is equal to 4. Okay, so we have solved for the values of a and q and its 4 marks, since we use the simultaneous equations and everything. Okay, then let's move on. We are asked to find the length of CD. So the length of CD from here to here. Okay, what do we have right now? What did I say? Was that q was equal to what? Was equal to c, remember? So we do have the coordinates of d, and then now we can find the coordinates of what? Of q. So of c. Basically, we've already found it because we have already calculated what is the value of q here when x is equal to 0. When x is equal to 0, it's gonna be number, let's see, 5.3.1. 5.3.1, x is equal to 0. And then, even though we don't need x, I just want to write the coordinates of c, and then y is equal to q, is equal to 4. So basically the coordinates of c is 0 and 4. Okay, is 0 and 4. 0 and 4. The coordinates of d is 0 and minus 3. And then so to basically find the length of CD, we just have to subtract these two coordinates, to find the distance from here to here, to find the distance from here to here. Let me see how can I explain it for you so that you understand. So, but it's basically the difference between the y values, so this is essentially a straight line going from here to here. It's not at an angle, but it's just a straight line because there is no change in the x values, or in the x values. There's no change. X is still x is still 0 here, x is still 0 here, but we do have a change in the y values. And then we are seeing here that here c is equal to cy, or the value of y at c is 4 and the value of y at d is -3. So in order to find the length of CD, we just have to subtract those two, just have to subtract those two in order to find the distance from C, or the length from C to D, from C to D, and it's 2 marks, you can see. So for our CD, length CD is equal to YC minus YD, starts with the positive one. YD is gonna be equal to what? What is our YC? Is 4 minus YD is equal to, it's minus 3, if I remember. That is our value of D. And then, so negative and negative is gonna be a positive. 4 plus 3 is equal to 7 units. Can be meters, it can be centimeters, but here we are not given anything, so we're just gonna say it's 7 units. And then what are we asked to find here is the equation of the straight line through A and D. Through A and D. Where is our A and D? Okay. Equation of the straight line through. So we are given 2 coordinates. Okay, this one doesn't fit perfectly, but you get the idea. But the straight line passes at A and D. At A and D. So yeah, this is the straight line that we are asked to find the equation for. And then remember, it's 5.3.2. The general equation 5.3.2 of a straight line is equal to y is equal to mx plus c, and then m is our trident. And remember, I said if we want to find a trident, we can use this formula, y2 minus y1 over x2 minus x1. So we do have 2 coordinates there, of which is coordinates A and coordinates D. So it's D is 0.0 and -3, and then for A, so for A, the coordinates of A are given. Or did we calculate them? I think we did. Coordinates of A is -2 and 0. So for D is 0 and -3, and then for A is -2 and 0. Hopefully I got that correct. Okay, we can start with any of the coordinates here. We can start with D, we can start with A. It doesn't make a difference. So M is equal to, what is y2? Y2, okay, let's just use the ones for D. It's gonna be -3 minus y1, let's just say 1. Okay, maybe for you to understand better. Okay, I can simply say equal to yd minus ya over xd minus xa. So it's -3 minus ya, which is y1, 0 in this case, over xd, 0 minus xa, of which is -2. And be careful of the signs. It's -2. We're putting -2 as it is. We are not changing anything. We're not gonna say just because there's a minus here, now we're not gonna include that negative for 2. Therefore, our trident is gonna be -3 minus 0. We're gonna have -3 over 0 minus -2. So it's a negative and negative, positive. So our trident is gonna be -3 over 2. Okay, we already have an M right now. So what are we going to look for next is the value of C. The value of C. Excuse me. The value of C. So we can simply use any of the coordinates here to find the value of C, but remember that the value of C is also what we call the y-intercept, whereby x is equal to 0. Y is equal to mx plus c, y is equal to minus 3 over 2 x plus c, So, so for our c, let's take any of the coordinates here. Let's just use that 0 and minus 3. Minus 3, the coordinates of t, minus 3 over 2 into 0 plus c plus c. And then our c value is equal to minus 3. Minus 3. We said c is a what? C is the y-intercept. Here, t. This is the first thing I think as we did. Where our graph cuts the y-intercept, whereby x is equal to 0. So it was basically the same thing, but just use the coordinates. We could have also used the coordinates of a. We are gonna find the same thing. Okay, so basically we have our equation right now. We're asked to find the equation of the line that passes through A and D. So let's rewrite everything. Therefore, y is equal to minus 3 over 2 x minus 3, since it's a negative sign there. So this is the formula that represents the relationship between the x and the y for this straight line, that we just drew here. Okay, next. For which values of x is f at x greater than 0? Is f at x greater than 0? F at x, let's come back to our graph. It's this parabola. Okay, is f at x greater than 0. So if they are saying it's f at x, so what they are saying is basically okay, this graph here, the parabolic function, whereby the parabolic function is greater than 0. So I just want to show you graphically first. So this is the parabolic function here, and you can see that the parabolic function here it's what? It's below 0. It's below 0. It's below the x-axis. So from here, going from B, going in that direction, this function is below 0, and we are looking for the values whereby the function is greater than 0. The same thing is true here. From here, going in that direction, the function is what? Is below 0. It's below 0. So basically, the function is only greater than 0 from here up until here. So let me maybe use a different color. This is the only time that the function is greater than 0. So going from basically from the coordinates of A to the coordinates of B, those are the x values whereby the function will be greater than 0, whereby the function is above the x-axis. As you can see here, I've highlighted that the function is indeed above the x-axis. Okay, so how do we answer that question? Where is it? Where f at x is greater than 0. Okay, so it's gonna be the coordinates of A. What are the coordinates of A? These are the coordinates of A. minus 2 and 0, and then the coordinates of P. The coordinates of P. I think we should have calculated them somewhere. Somewhere. Okay. The coordinates of P, but they are basically gonna be the same as the coordinates of A, because these are both the intercepts. These are both the intercepts. They are basically gonna be the same, just a different sign. Just a different sign. So it's gonna be, I think here for the coordinates of A, sorry. The coordinates of A, we have a what? We have minus 2 and 0. Then for the coordinates of B, we're gonna have what? We're gonna have 2 and 0. So they're basically the same. These are the coordinates of B, because both of these are the intercepts. So our parabolic function is above 0, whereby x is greater than minus 2, whereby x is greater than minus 2, and then also whereby x is less than 2. Okay, so we can just rewrite this as this: x is greater than minus 2 and x is less than 2. So we're just gonna rewrite this like this. So it's x is greater than minus 2, or x is less than 2. Okay, where f at x is decreasing. Where f at x is decreasing. So for when the function of f at x is decreasing, so we do have this function that is facing down, where the f at x is decreasing, and then it's 1 mark. F at x is decreasing. Where f at x is decreasing. And remember what I said about the functions being continuous. Is that this, as much as it is facing down, it is also going in a what? In this direction, and it's also going in a what? In this direction. So it's decreasing here, as the function is going in the positive, what we call this thing, positive x values. It's getting bigger and bigger as x is getting bigger and bigger. Why? What is happening? What is happening to the function? It is increasing. Sorry, it is decreasing. It is decreasing here. As the function is going in that direction, it is also going in this direction. It's getting smaller and smaller. So basically, what we can say here, and then what do we have? Go on this direction, the function is decreasing in both sides, and then so you can see whereby f is decreasing, whereby the function is decreasing, is whereby this could be representing also the trident, because we only have to consider the values from 0 going up, going into the positive x values, going to the x values. But basically what I'm trying to say is that our function is decreasing in this side. It's decreasing in this side. It's a negative slope. The function is decreasing this side from what? From 0. From 0 there, going into the positive x direction. So just to answer that, we're gonna say what? It's where x is greater than 0. That is where our function is decreasing. So this will mark the end of our lesson. I can see that we are already 13 minutes late. I just wanted to cover this question. We will do more examples on our oncoming session. I think it's gonna be on Thursday. We're gonna do more examples on functions, and we hopefully also gonna be able to touch on hyperbolic functions, and yes, some other just more examples, and maybe even simpler examples, and then more exam questions, but all in all, thank you for joining this meeting, guys. Thank you for joining this meeting. Hopefully you learned something today, and hopefully the meeting was indeed fruitful. If you have any other question, I would like to ask you to send them on the group, maybe regarding this, regarding what we did today, or maybe even other questions that you would like me to tackle during our next lesson. Please just send them on the group. And thank you for attending.